PC gaming used to work in a very simple and easy to understand way. The CPU was the brain of the whole system. It handled everything happening inside the game world, such as physics, enemy movement, player actions, and all the game logic. Once the CPU finished calculating all of that information for one frame, it passed that data over to the GPU. The GPU then took that information and drew every single pixel on your screen from scratch. Every image you saw was real and complete. Nothing was faked or invented. The GPU built each frame honestly at your full screen resolution, and the result was a direct and truthful reflection of what your hardware actually calculated. This is how things worked for decades, and nobody questioned it, because it made perfect sense. This system made the CPU extremely important for gaming performance. The GPU could only go as fast as the CPU allowed it to. If your CPU was slow, the GPU had to sit and wait for data before it could do anything useful. If your CPU was fast, the GPU stayed busy and produced more frames per second without interruption. This is why gamers always invested heavily in fast processors with high clock speeds. A weak CPU would slow down even the most powerful and expensive GPU in the world. Both chips worked as equal partners, and neither one could carry the whole system alone. PC building guides always repeated the same advice, which was to balance your CPU and GPU carefully and never let one fall too far behind the other, because the weaker one would always hold the stronger one back. Games were also designed and built with this system in mind. Developers wrote their game engines, assuming the CPU would handle all the simulation work and the GPU would handle all the drawing work. Everything flowed in one clear direction. The CPU calculated the game world, and the GPU drew it on screen. If you wanted 60 real frames per second, your hardware had to genuinely produce 60 complete and fully rendered frames every single second. There was no shortcut and no alternative method. Performance was always a direct and honest reflection of how capable your hardware actually was. More powerful hardware meant better performance, and weaker hardware meant worse performance. It was straightforward and transparent. A few years ago, NVIDIA introduced a technology called DLSS, which stands for Deep Learning Supersampling. When it first appeared, it seemed like a small and modest improvement, just a way to squeeze out a little extra performance without losing too much visual quality. Most people did not think it would fundamentally change how gaming worked at a deep level. It seemed like a convenience feature rather than something revolutionary. But with each new generation, DLSS became more powerful, more accurate, and more capable than the version before it. By the time DLSS 4 arrived with the RTX 50 series graphics cards, something very significant had happened beneath the surface. The entire idea of how a game produces its final image on your screen had changed completely, and the old rules no longer applied in the same way. Here's how DLSS works explained in simple and plain terms. Instead of rendering the game at your full monitor resolution, the GPU first renders it at a much lower internal resolution. If your monitor displays at 4K, the game might actually be drawn internally at 1080p, or sometimes even lower than that. That rough and low resolution image is then passed through an artificial intelligence model that runs on special chips inside the GPU called tensor cores. This AI model has been trained on an enormous number of game frames from many different games and many different visual scenarios. It has learned how to take a blurry and low-quality image and reconstruct it into something sharp, detailed, and visually clean. The final image that comes out of this process is then shown on your screen at full 4K resolution, and it looks like it was always that sharp and detailed. The part that truly surprised people was that this AI reconstructed image is not just acceptable or passable quality. In many real-world tests and direct comparisons, DLSS 4, its quality setting actually matches native rendering, and in some situations, even surpasses it in sharpness and visual clarity. The reason for this improvement is that DLSS 4 uses a newer and significantly smarter type of AI architecture called a transformer model. This model can look at a much wider area of the image at once and understand the visual context far better than older and simpler AI methods could. It handles difficult fine details like strands of hair, small leaves on trees, distant buildings, thin wires and fences with much more accuracy and stability than anything before it. This is the moment where everything changes in a fundamental and philosophical way. If an AI's rebuilt image consistently looks as good as or better than a natively rendered one, then there's no longer any strong or logical reason to insist on native rendering. The old belief that native rendering was always the gold standard and the honest, correct way to produce game graphics quietly starts to collapse under its own weight. Frame generation then pushed things even further than DLSS alone, and this is the technology that most directly and clearly makes the CPU secondary in the gaming pipeline. Frame generation works by creating additional frames using artificial intelligence rather than actually rendering them through the traditional pipeline. Between every real rendered frame, the AI generates extra fake frames by carefully studying how objects and surfaces are moving across the screen and then predicting and drawing what the next moment in between should look like. With the multi-frame generation feature in DLSS 4, the GPU can now generate up to 3 completely AI-created frames for every single real frame it actually renders through the traditional method. What this means in practice is remarkable. Your CPU might only be simulating and calculating 60 real game states every second, but your screen can display what looks and feels like 240 frames per second to your eyes. The extra 180 frames were never touched by the CPU. They were entirely invented and constructed by the AI, running on the GPU completely independently of the CPU simulation. This single change destroys the old relationship between CPU speed and gaming frame rate that existed for decades. In the traditional system, getting 240 frames per second in a demanding game required an extremely fast and very expensive CPU, because the processor had to genuinely calculate 240 complete and accurate game states every single second without any shortcuts. That was an enormous and punishing workload that only the most powerful and costly chips could handle. Today, with frame generation, a perfectly ordinary mid-range CPU running at a comfortable 60 simulation steps per second is completely sufficient. The AI running on the GPU handles all the visual frame multiplication by itself. The CPU is no longer the limiting factor that determines how smooth and fast your game looks and feels on screen. This reality completely changes the practical advice for anyone building or upgrading a gaming PC right now. The old rule that everyone repeated was to always invest seriously in a powerful CPU and balance it carefully with your GPU. That advice was correct and sensible when the CPU was the thing directly driving your frame rate. Today, that advice is outdated. A mid-range processor is genuinely and honestly sufficient for the vast majority of gaming situations when it is paired with a modern RTX graphics card. The money that gamers use to spend chasing a flagship CPU for better gaming performance would produce far better and more noticeable results if that same money went toward a more powerful GPU with a higher tensor core count. Those tensor cores are what run the AI models behind DLSS and frame generation, and they are now the single most important piece of hardware in a gaming system for determining what your games actually look like and how smoothly they run. There is, however, a genuine and serious concern that comes alongside all of this impressive progress. When game developers know that AI will automatically fix their image quality and multiply their frame rate. Some of them begin putting less time and effort into properly optimizing the actual game engine. If DLSS will smooth over rough edges and unstable images, then why spend months carefully optimizing the rendering pipeline? The result of this thinking is already visible in some games today. They look noticeably rough, blurry, and unstable at native resolution with all AI features disabled. The AI has quietly become a cover for poor and lazy optimization rather than a bonus in properly optimized game. This creates a damaging cycle where native rendering quality gets progressively worse over time, and AI assistance becomes more and more necessary just to make games look and run acceptably well. AMD has its own competing answer called FSR4, and Intel has a technology called XeSS. Both of these alternatives work across a wider range of graphics cards, including non-NVIDIA hardware, which is a real and meaningful advantage for consumers. However, in terms of actual output image quality, independent testing consistently and clearly shows that DLSS 4 produces sharper, more stable, and more accurate results than both competing alternatives at equivalent settings. The larger and more concerning issue is that NVIDIA multi-frame generation is exclusively available on RTX 40 and 50 series graphics cards. No AMD graphics card, no Intel graphics card, and no older generation NVIDIA card can access this feature at all. As multi-frame generation becomes more central to how games are designed and how performance is measured, being permanently locked out of it becomes an increasingly serious disadvantage for a large portion of PC gamers. Native rendering is not completely gone today, but its position as the dominant and default standard is clearly and permanently ending. The honest pixel-by-pixel method that defined PC gaming graphics for so many decades has been pushed aside by AI construction as the primary way of delivering high-quality visuals at high frame rates. Most of what you see on screen in a modern game running on current RTX hardware is no longer natively rendered in the traditional sense. It is reconstructed, upscaled, or outright invented by artificial intelligence. The CPU, which was once the engine that the entire gaming experience depended on, has been repositioned as a background supporting player. It still matters for game simulation, open-world streaming, enemy AI behavior, and physics complexity. But it no longer drives the visual output that actually appears on your display. That responsibility now belongs entirely to the GPU and the AI models running inside it on dedicated Tensor Core hardware. The old contract between CPU and GPU that defined PC gaming performance for a generation has been completely and permanently rewritten, and in this new version, the GPU won decisively.